Okay, let's talk about buffers and titration curves. All right, so before we can really understand buffers, we have to understand something called the common ion effect. So the common ion effect is basically just a consequence of Le Chatelier's principle, which we talked about when we discussed equilibrium. So when I have a weak acid, and I take a salt containing that anion. For example, if I had hydrofluoric acid HF and I added sodium fluoride, it's going to reverse the dissociation of the acid because in that equilibrium system, when I add the conjugate base, I've added a product. So it's going to shift equilibrium back to the reactant side. And therefore, it lowers the percent dissociation of the acid. You can do the same thing if you use the conjugate acid of a weak base. And these solutions are known as buffer solutions. And they're buffers because they resist changes in pH. So let's talk about some characteristics of buffer solutions. So it resists a change in pH, as I said, and so we would say that it's pH stable. We can use a weak acid in its conjugate base. We can use a weak base in its conjugate acid. And we can make a buffer of any pH by varying the concentrations of the acid base and its conjugate. You don't have to know how to do those calculations, but we do something called the Henderson-Hasselbalch equation. All right, so how does a buffer resist pH changes? Let's look at some examples. All right, so let's look at an acidic buffer solution. So let's say that we created a buffer with equal volumes of 0.1 molar methanoic acid and 0.1 molar sodium methanoate. So that means that it's formed from methanoic acid, it's been deprotonated, and then it's combined with sodium. Okay, now, here's how we would write an equation for that. So we are showing methanoic acid dissociating into hydrogen ions and the methanoate ion. Now you might notice that I talked about sodium methanoate, but I didn't include sodium in here. That's because sodium's only function is to form a salt with the anion. Okay, so we don't actually particularly care about sodium in this equilibrium. It's just a spectator ion, it's not participating. All right, so what happens if I add acid? All right, now you may remember from equilibrium that if I add a product, it's going to shift the equilibrium. The equilibrium will shift to reactants to balance back out, okay? So essentially, as I add more acid, it's going to combine with the conjugate and shift equilibrium back this way, okay? So the excess acid that I've added is just going to be consumed. It's going to go back into undissociated acid, and then it'll keep the pH stable. Now, if I add base in the form of hydroxide ions, the hydroxide is going to react with the hydrogen ions, creating water. What I'm effectively doing when that happens is removing the hydrogen ions, and so the system will respond by shifting to products to replace those ions. So again, the pH is going to stay pretty stable because the system's just going to shift to replace those, and so the pH should stay roughly the same. Now, eventually, depending on the concentrations, you can add enough acid or base so it will exhaust the buffer, as we say. It'll just run out of stuff to react with. But small amounts of acid base. Let's look at a base buffer system. So we could create a buffer with equal volumes of ammonia and ammonium chloride. And let's just say these solutions were of equal concentration. Doesn't matter what they are. Okay, so this would be the equation we would use to represent this. And again, the ammonium chloride, we don't really care about the chloride ion. It's just a spectator. The ammonium is what we care about because it's the conjugate acid of the weak base. Okay, so if I add acid, it will react with the hydroxide ions to produce water, thereby removing a product, and equilibrium will shift to the product side, replacing the hydroxide and keeping the pH stable. If I add hydroxide, well, then I'm adding a product, so it's going to shift the equilibrium to the reactant side. Okay, so that will basically get rid of the excess hydroxide and again keep the pH stable. All right, so there's a couple different ways that we can make a buffer. So the way we sort of talked about is taking a weak acid or base and adding a salt of its conjugate to the solution. So again, some examples would be ethanoic acid and potassium ethanoate. That would create a buffer. Or we could use ammonia and ammonium chloride. Another thing that we can do is we can take a weak acid or base and use enough of a strong base or acid to partially neutralize. All right, so what that does is when it partially neutralizes it, it takes the undissociated acid and creates the conjugate. So instead of adding a salt with the conjugate, we're just creating it by partially neutralizing. So for example, if I used 50 milliliters of 1 molar methanoic acid and 25 milliliters of 1 molar sodium hydroxide, that would dissociate half of the methanoic acid into its conjugate. All right, so this is a sample IB question. These are kind of a mess because of all these units. It just looks kind of sloppy. So go through one by one, see which ones you can eliminate, and see if you can figure out what the correct answer is. So pause for a sec, try this, and then we'll go over it. Okay, now when we're looking at ones we can eliminate here, we can automatically eliminate A and C, because A and C both involve a strong acid and a strong base, and we can't have that, right? That's not going to create a buffer. We need a system at equilibrium, so we need a weak acid or base. All right, so B or D both have a weak acid and sodium hydroxide. So what we need to do is find the one where the weak acid is only partially neutralized. So in B, they're the same concentration, but we have 100 milliliters of the ethanoic acid and only 50 of the sodium hydroxide. So that should be partial neutralization. In D, we have more sodium hydroxide than we have weak acid, so it's going to completely neutralize it and we won't have a buffer. So the correct answer is B. All right, here's another practice IB question. This one's a little bit different because it specifically says that we're using equal volume of the solutions. Okay, so that's pretty significant. So pause for a sec, try this, and then we'll go over it. Okay, so same thing we did last time. We're going to rule out right away anything that doesn't have a weak acid or base. So A is a strong acid and a strong base, so we can rule that out. B is a strong acid and its conjugate, but that doesn't create a buffer solution. So C and D both have a weak acid. But here, C is not possible because if they're equal volume and concentration, the potassium hydroxide will completely neutralize the propanoic acid. So the correct answer has to be D because we have a weak acid and a salt containing its conjugate. All right, so let's talk about titration curves. So a titration curve is just a graph that shows the pH versus the volume of acid or base added. Whether we use acid or base will depend on what was in the burette and what was in the Erlenmeyer flask. Now, one thing that you'll notice as we look at these is the pH shows a really sudden, sharp change near the equivalence point. The equivalence point is where the moles of hydroxide are equal to the moles of the hydronium ion. So acid and base are equal. All right, so let's look at a strong acid, strong base titration curve. All right, so we have milliliters of base added on the x-axis and pH on the y. All right, so at the equivalence point, which it can be represented as V subscript EQ, the volume at equivalence, the moles of hydronium are equal to the moles of hydroxide. Now, one thing you'll notice is that there's a really sharp rise in pH as we approach the equivalence point. And you have to really think carefully about what is going on in the titration flask to understand why this is. And it also helps to remember that pH is a logarithmic scale. So initially, when I have my acid and I'm adding drops of base, the amount of base in each drop is really small compared to the amount of acid in the flask. But as I neutralize more and more and more and the concentration of acid goes down, the pH won't have changed tremendously. When I go from pH 1 to 3, that's 1 is 100 times more concentrated. You don't see a huge change in pH, but there's a big change in the concentration of the acid. Then all of a sudden we get to a point where the acid is very dilute. And remember, we're adding base here. So the base concentration is the same as it has been since the beginning. So all of a sudden, the amount of base in each drop used to be really small compared to acid. All of a sudden, the amount of base in each drop is really large compared to the acid in the flask. So what we see is all of a sudden the pH jumps up very, very rapidly. Okay? With a strong acid and a strong base, the equivalence point is at pH of 7. And that's because the salt produced by a strong acid and a strong base, you'll recall from the last topic, is neutral. And again, neither the conjugate base nor the conjugate acid is strong enough to affect the pH. Okay, now let's look at a weak acid, strong base titration curve. Now right away, you probably notice the shape is a little bit different. So we have a more gradual increase in pH as we approach the equivalence point. And with a weak acid and a strong base, the equivalence point is higher than 7. And that's because the salt that's formed is basic, because the strength of the conjugate base is strong enough to pull the pH over 7. Now, an interesting thing is that we can do with this titration curve is we can use this titration curve to find the pKa of our weak acid. At the half equivalence point, so the equivalence point is at 25 milliliters, so the half equivalence point would be at 12.5 milliliters. At the half equivalence point, half of the acid has been dissociated, right? That makes sense because at the equivalence point, all of it has been. Now, what this means is that pH equals pKa at the half equivalence point. So let me show you why. All right, so as we just said, when half of the weak acid has been neutralized, that means half of it has been converted to the conjugate. All right, so if this is our weak acid system, what that means is that the concentration of the undissociated acid is equal to the concentration of its conjugate. Okay, so if this is the expression for Ka and the conjugate and the acid concentrations are equal, they will cancel out. So we can say that Ka is equal to the concentration of hydrogen ions. We can take the negative log of both sides, and we know negative log, P means negative log, so pKa is equal to pH. So let's delve a little into the shape of these pH curves. All right, so we have something called the buffer region when we have a weak acid titrated with a strong base. So this is the range where the pH change is minimal, but you see a slight gradual change. So initially we see a sharp pH rise when the base is added, okay? But after we've added a little bit of base, we've created the conjugate base of the weak acid, which makes a buffer with the weak acid and its conjugate. So at that point, the pH change is very gradual until the buffer is exhausted. So once we run out of the undissociated acid, and then we see the linear region. And this occurs in both the weak acid and the strong acid titration curves. So there's a sharp increase when neutralization occurs. And again, this is because at this point, the acid is very dilute. So each drop of base then contains a lot of moles of hydroxide compared to the moles of hydrogen ions. So this is why we're going to see a dramatic change in pH. And again, you also have to remember it's a logarithmic scale. So when we get up to pH of 5, for example, the concentration of hydrogen ions is 10 to the negative 5th. So if we had a 0.1 molar solution of base, that's quite a lot of moles of base compared to the moles of acid in the solution. Okay, so let's compare these strong and weak acid curves. First, in terms of shape. So the strong acid curve is going to be a lot smoother. There's almost no rise, a dramatic rise, then it levels out quickly. In the weak acid curve, we have the more gradual rise with that buffered region, and it typically starts at a higher pH if we had the same initial acid concentrations because the weak acid is only partially dissociated. The pH at equivalence point for a strong acid, strong base, it would be at 7. For a weak acid, strong base, it'll be above 7 because of the salt that's produced. And in a strong acid, weak base, it would be below 7. The total volume at equivalence point. So if we have a strong acid and a weak acid solution of equal concentrations, the total volume at the equivalence point should be equal, okay? And that's because it takes the same number of moles to completely neutralize them. If I look at these two expressions, or equations, I have hydrochloric acid reacting with sodium hydroxide to produce water and sodium chloride. And then I have methanoic acid reacting with sodium hydroxide. These are still all 1-to-1. If we think about this in terms of mole ratios, we need the same number of moles of base to neutralize each of those. So the total volume at equivalence point for acids of the same concentration should be equal. All right, so let's look at this titration curve of a weak acid with a strong base and sort of see what we could pull away from this graph. All right, so first, we could figure out the pKa of the weak acid because it's equal to the pH at half equivalence point, so roughly 4.5. And we can also see how much base was required to neutralize the acid. And then we could use the titration formula to calculate the molarity of the acid. All right, so we used 20 milliliters of the weak acid, and we titrated it with 0.1 molar potassium hydroxide, and it took about 20 milliliters to titrate it. All right, so the number of hydrogens times the molarity of the acid times the volume of the acid equals the number of hydroxides times the molarity of the base times the volume of the base. So we would see that since it's a monoprotic acid and a base with only one hydroxide, and we used equal volumes, the concentrations are also equal. Okay, last thing we want to talk about is indicators. So an indicator is a weak acid or base, and in an indicator system, the undissociated acid and its conjugate are different colors. Right, so here's an equation to represent that. If Hin is the general formula for an indicator, that would have color 1, and the dissociated part of the indicator would be color 2. All right, so what makes a good titration indicator? How would we pick one? Because there's quite a large number of indicators that we could use. So first, we needed to change color in the range of the equivalence point, right? Otherwise, it's not going to be very useful to us. Now, it does not have to be completely exact. Let's think about why this would be. So there's a really large linear region. So as long as the color change occurs in that region, it should be a suitable indicator. Now, indicators generally change color within 1 unit of their pKa. So if you're given the pKa or the Ka of an indicator, you could decide whether or not it would be suitable. And in table 22 of the data booklet, there's a whole list of indicators and their pKa values. So these are just some sample indicators and their color changes. The one you've used the most is phenolphthalein, and we're going to talk about why that is in just a minute. But there's a whole wide range of indicators at different pHs. Now, let's think about this. When we look at the equivalence point of phenolphthalein, we use this for strong acid-base titrations all the time. So why can we use this even though its range is slightly above 7? So when we look at phenolphthalein, it changes in the sort of 8 to 9 range. So why can we use this? Well, it's still within the linear region of that titration curve. So it's still going to change at the same time as it would if its equivalence point was at 7. And now why do we use phenolphthalein instead of bromothymol blue or thymol blue, which change in roughly the same range? The color change for phenolphthalein is colorless to colored, so it's a lot easier to tell when it's changed. For bromothymol blue and thymol blue, if you look back, thymol blue goes from yellow to blue, and bromothymol blue also goes from yellow to blue. So there's this point where you're like, is it green, is it yellow, is it blue? And it can be a little more subjective, where if it goes colorless to colored, it's a lot easier to tell. Okay, so practice with these, look at a lot of titration curves, and we will make some in class as well.